This video is concerned with some basic techniques of data analysis. Most of it is recall, material that we've covered before. We've covered empirical distribution functions, sample quantile functions, histograms and kernel density estimators, and we'll add a bit more detail here and there. We also introduced QQ plots, which are a means of visually comparing two distributions. So let's start looking at empirical distribution functions. Suppose that we have a sample x1 up to xn of independent draws from a common distribution f. Then the empirical CDF, or ECDF, denoted by f hat, is a non-parametric estimator of that distribution function. It is defined as follows. Here we define the indicator of the random variable xi less than or equal to x, and this is switched on to 1 if the ith sample point is less than x and 0 otherwise. So this is a discrete random variable which takes two values. The ECDF is denoted as follows: f hat n. The subscript n indicates that we're dealing with a sample of n points, and the ECDF evaluated at the point x is simply the average of all of these indicator functions. That means that it's equal to the proportion of sample points which lie below the value little x. Now observe that the value f of x is just a number, f is just a function, whereas f hat of x is actually a random variable because it's a sum of random variables. Also observe, and I will leave this as an exercise, that the expected value of the indicator is just equal to f of x, and the variance of the indicator is the product of f of x with 1 minus f of x. This is a simple exercise which involves the means and variances of discrete random variables. It follows in particular that the expected value of f hat is equal to f. In other words, f hat n of x is an unbiased estimate of f of x, and the variance f hat n x is equal to f of x 1 minus f of x over n, and that will go to 0 as n goes to infinity. This means that the random variable f hat of x is a random variable whose mean is f of x and whose variance goes to 0 as n goes to infinity. In other words, the random variable lies closer and closer to f of x as the sample size increases, in other words, as n goes to infinity. Here we show the ECDF of 15 draws from the standard normal distribution. What we have here therefore is a stair function or a step function, and this step function has 15 steps, a step at every one of the sample points. The standard normal CDF is shown in blue here, and as you can see, the rate function is an approximation of the blue function. As the sample size increases, the ECDF will more and more closely approximate the actual CDF. As was illustrated by the previous slide, the ECDF of some observations x1 up to xn is always a discrete CDF. In other words, it's always a step function. It will put a mass of 1 over n at each of the observation values xi, where n is the number of observations. So if you order the data points from smallest to largest, in other words, x1 is the smallest data point, x2 is the second smallest, etc., then the ECDF will be a step function with a jump of size 1 over n at each data point. If two of the data points happen to be the same, for example, then there will be a jump of size 2 over n there. Now, a random variable x hat has the same CDF as the empirical CDF, if and only if its CDF, which is just a probability that x hat is less than or equal to x, is equal to the empirical CDF, which is defined as shown here. Such a random variable x hat is discrete even if the original distribution f is a continuous distribution. Its probability mass function will therefore be given as follows: little f hat x is thus the probability that x hat is equal to x, and that is the number of observations xi which are equal to x, divided by n. Typically, if f is a continuous distribution function, then there is at most one observation xi which is equal to x. Now suppose we want to estimate the expected value of a function of the random variable x. One obvious way to do this is to use the approximation x hat. And the expected value of g of x hat is simply equal to 1 over n times the sum of g of the values of the observations. In other words, it's the average of g evaluated at the observations. Now the type of statistical estimator that we have here, where instead of using the true CDF f, we use instead the empirical CDF to compute the expectation, is called a plug-in estimator. We'll have more to say about that in the lesson on statistical estimation. Next, a reminder about quantile functions and sample quantile functions. The quantile function associated with the distribution f is denoted by f inverse. For a number p between 0 and 1, in other words for a probability p, the pth quantile of a distribution is defined as follows. F inverse p, or the quantile function evaluated at p, is the least y for which the distribution function evaluated at y is greater than p. We then showed that f of q is less than or equal to p if and only if q is less than or equal to f inverse p. If f is strictly increasing and continuous, then f of q is equal to p if and only if p is equal to f inverse q. Now observe that f inverse p is only defined for p between 0 and 1 because p is a probability. As you can see over here, p is a value that the distribution function can take, and the distribution function takes values between 0 and 1 only. Now if we have a sample of data points x1 up to xn say, then this pth sample quantile is defined in exactly the same way, but we use the empirical CDF instead of the true CDF. So it's a plug-in estimator for the pth quantile of the distribution f because we're using the empirical distribution instead of the true distribution. Suppose we order the data points x1 up to xn from smallest to largest. Recall that the CDF is a step function, and so the value of the sample quantile function at the point p will be the first data point for which the ECDF jumps to a point which is greater or equal to p. Let's illustrate this. Here we have a sample of data points 5, 2, 1, 3, 4, which if we reorder them from smallest to largest, it's just 1, 2, 3, 4, 5. So we expect the ECDF to have a jump at each of the integers 1, 2, 3, 4 and 5, and the jump size will be 1 over 5. As you can see, this is exactly what happens. We have a jump size of 0.2 over there, 0.2 over there, etc. Now suppose we'd like to compute the quantile function at the point 0.25. What we do is we go to 0.25 on the y-axis, and we find the first point on the x-axis where the CDF jumps over 0.25. And as you can see, that is at the point 2. So the quantile function evaluated at the point 0.25 is 2. Note that the ECDF is a right continuous function. So if we look at the graph on the right, we have a look at the quantile function. At the point 0.25, the value of the function is 2. Note that any horizontal line on the graph of the ECDF corresponds to a vertical line on the graph of the quantile function. For example, here we have a line going from 1 to 2 on the x-axis at height 0.2, and it corresponds to a line at the point 0.2 going from 1 to 2 on the y-axis. Similarly, we have a line here at x is equal to 2 from 0.2 to 0.4 on the y-axis, and that corresponds to a line over here from the quantile function. Thus the graph of the quantile function is simply the graph of the ECDF reflected in the line y equals x. Next, we consider quantile-quantile plots or QQ plots. As I have already mentioned, these are a way of visually comparing two distributions. Suppose two random variables x and y have the same distribution. In that case, they have the same cumulative distribution function, and by the way the quantile function is defined, they must also have the same quantile functions. Now a quantile-quantile plot or QQ plot is a convenient visual tool for comparing the two distributions. It consists simply of all the points quantile function of x evaluated at the point P and the quantile function of y evaluated at the point P. So we have here an ordered pair consisting of the quantile functions evaluated at the same points P. If x and y have the same distribution, in other words they have the same CDFs, then they will have the same quantile functions, in which case this point will be equal to that point, in other words the x-coordinate will be equal to the y-coordinate, and so the plot will lie on the straight line y equals x. If the QQ plot deviates from the line y equals x, then x and y do not have the same distribution. Now MATLAB has this built in. The function QQplotXY will construct a QQ plot of the sample quantile functions of two datasets x and y. QQplotX will compare the sample quantile function of x with that of the standard normal distribution. And QQplotXPD will construct a QQ plot of x and a probability distribution object PD. So have a look at MATLAB's documentation to learn more about probability distribution objects. But for example, to make a probability distribution object which is gamma 5,2 distributed, you use PD equals makedist gamma 5.5. So let's see how a QQ plot works. Here I'm going to generate two data vectors, x and y, and they're each going to be drawn from the standard normal distribution, 1,000 point each. As you can see here, there are 1,000 points. Well, it's truncated. And now I'll simply draw a circle at each of the points quantile xp and quantile yp for p between 0 and 1 in steps of 0.05. So I'll be drawing 20 circles. And as you can see, they lie more or less along a straight line, which indicates that these distributions are related. And if I plot the line y equals x, you can see that they lie along this straight line. In other words, we can deduce from this that x and y come from the same distribution, which we already knew. Next, I'll generate data from the standard normal distribution and the t-distribution with 3 degrees of freedom. Again, we have 1,000 points and we're going to draw a QQ plot with 20 points on it. As you can see here, they deviate significantly from the straight line, and therefore the two distributions are not the same. In the code here, I've drawn each point individually using a for loop. Of course, this is not the most effective way of doing it. It's just to make the point that the QQ plot is nothing but a plot consisting of the quantiles of two distributions evaluated at the same value p between 0 and 1. If I increase the number of points to say 100 points, the QQ plot would look like this. Here's a QQ plot of the returns of the S&P 500 index versus the standard normal distribution. The returns have also been standardized. In other words, their mean is 0 and their variance is 1, which is accomplished in the usual way by subtracting the mean and dividing through by the standard deviation. As you can see, the returns do not lie along the straight line y is equal to x, and therefore we can deduce that the returns of the S&P 500 aren't normally distributed. We'd like to investigate now what the shape of a QQ plot can tell us about the distributions. Now suppose that we have a random variable x and also an affine combination of x, namely another random variable of the form ax plus b. Let's have a look at what the QQ plot of x and ax plus b actually looks like. Firstly, notice the following relationship. The quantile function of ax plus b, evaluated at the point p, is equal to a times the quantile function of x at that point plus b. This is a very nice relationship. To see why this is true, suppose that q is equal to the quantile function of ax plus b at the point p. Well, that means that the CDF of ax plus b at the point q is equal to p. By definition of CDF, the CDF is just the probability that ax plus b is less than or equal to q. So all of that is equal to p. Now we're assuming here that a is greater or equal to 0, so if we subtract b and we divide through by a, we get that the probability that x is less than or equal to q minus b over a is equal to p. That says that the CDF of x evaluated at the point q minus b over a is equal to p, and therefore the quantile function of x evaluated at p is equal to q minus b over a. When we rearrange this, we see that q is equal to a times the quantile function of x evaluated at p plus b, but q started off being the quantile function of ax plus b at that point, and therefore these two values are the same. In other words, the point quantile function of x at p and quantile function of ax plus b at p is equal to the point quantile function of x at p a times the quantile function of x at p plus b. These are exactly the kind of points that lie on a QQ plot. And if we look at this second point over here, we see that the y coordinate is a times the x coordinate plus b. And thus all of the points on the QQ plot lie on the line ax plus b, in other words on the straight line with slope a and intercept b. In particular, if x has a quantile function f inverse x, then the standardized version of x is the random variable y, which consists of x minus mu x over sigma x, and that is an affine combination with a equal to 1 over sigma x and b equal to minus mu x over sigma x. And so the quantile function of y will look like the quantile function of x minus mu x divided by sigma x. And hence the graph of the quantile function of y is simply a scaled and shifted version of the graph of the quantile function of x, maintaining its shape. Let's illustrate this here. Here we have a is equal to 2 and b is equal to 3. We draw 1,000 points from the normal distribution, and we also draw 1,000 points from a times the normal distribution plus b. So the points that we obtain here are 1,000 points each. Now again we draw a quantile plot, and we get a line, but it's not the line y is equal to x. However, it is on the line 2 star x plus 3, as you can see. Here we see a QQ plot of the standard normal distribution versus the T3 distribution. Recall that the T3 distribution has much heavier tails than the normal distribution. We will be able to glean this fact from the shape of the QQ plot. Now for the QQ plot we have just shown, let x be standard normal and let y be standardized T3. Recall that the distribution function of x evaluated at q is equal to p if and only if the quantile function of x evaluated at p is equal to q. That's the case for distribution functions which are strictly increasing and continuous, which is the case here for both the random variables x and y. In particular, it follows that fx, f inverse x, p is equal to p. For small p, in other words for p on the left, near 0, the QQ plot lies below the line y is equal to x. In other words, we have that the quantile function of y lies below the quantile function of x. Now suppose that q is defined to be the quantile function of x at p, where p is near 0. Then the probability that x is less than or equal to q is just the distribution function of x at q, which is p. And that's the same as fy inverse p. which by definition is the probability that y is less than or equal to the quantile of y evaluated at p. But the quantile function of y at p is less than or equal to the quantile function of x at p, so the probability that y is less than or equal to the quantile of y at p is less than or equal to the probability that y is less than or equal to the quantile of x at p. The quantile of x at p is just equal to q, and so we see that the probability that x is less than or equal to q is less than or equal to the probability that y is less than or equal to q. And that means that the left tail of y is heavier than the left tail of x. So shown here are two density functions, one in red and one in blue. Recall that the probability that a random variable is less than or equal to q is equal to the area under the density function from minus infinity to q. Now for the normal distribution, the probability of being less than q is less than that for the t distribution. In other words, the normal distribution must be given by the blue curve, where the area under the curve is smaller. The red curve therefore is the density function of the T3 distribution. As you can see, this illustrates that the left tail of the T3 distribution is heavier than the left tail of the normal distribution, because the area under the curve of the T3 distribution is bigger than the area under the normal distribution. For large p, in other words for p close to 1, the QQ plot lies above the line y is equal to x. In other words, the quantile function of y lies above the quantile function of x. And you can follow the argument here to show that in that case the right tail of y is heavier than the right tail of x as well. And thus the T3 distribution has both a heavier left tail and a heavier right tail than the normal distribution. Since both distributions are symmetric about 0, this is not surprising. Let's consider this argument in a slightly more general setting. Suppose that we plot a QQ plot of two distributions f and g. In other words, we plot the points f inverse at p and g inverse at p for values p between 0 and 1. Now suppose f has a heavier right tail than g. Then the quantile function of f grows faster than the quantile function of g as p gets closer and closer to 1. And therefore the quantile function of f is greater or equal to the quantile function of g for values p near 1. Now the quantile function of f is the x-coordinate of the QQ plot, and the quantile function of g is the y-coordinate of the QQ plot, and so we see that the y-coordinate is less than or equal to the x-coordinate, and so this point here has a y-coordinate which is less than its x-coordinate. In other words, it lies below the line y is equal to x, and thus the QQ plot goes below the diagonal as p goes to 1, in other words on the right. Similarly, if f has a heavier left tail than g, then we see that the quantile function of f is decreasing faster than the quantile function of g, and therefore in this case the x-coordinate is smaller than the y-coordinate, and therefore the QQ plot goes above the diagonal on the left. The opposite is true if the tails of f are lighter than those of g. Now let's look at non-parametric ways of density estimation. Most of this material has been covered in lectures before. Firstly, we look at histograms. Suppose that we have independent rules x1 up to xn from a common distribution f. We can then divide the range of the data into bins, with each bin being an interval of real numbers, and above each bin we can plot a rectangle of height equal to the proportion of observations in the bin divided by the bin width, where the proportion of observations in the bin is simply equal to the number of observations in the bin divided by the total number of observations. In that case, as you can easily verify, the sum of the areas of those rectangles is equal to 1, as for a PDF. We can therefore think of a histogram as a representation of the distribution of the sample data, and it can be viewed as a non-parametric estimator of the corresponding density function. Now the choice of bin width is very important. Most software will do this for you automatically, but you may occasionally need to play around with the bin width. If the bin width is too large, then the distribution of the data will seem too smooth. If it's too small, then it will seem too ragged. We'll have similar problems when we look at kernel density estimation, as we will see. Here, for example, we've taken 1000 rows from the standard normal distribution and we've plotted a histogram, as well as the PDF of the standard normal distribution in red. And as you can see, the histogram closely follows the PDF. However, if we change the number of bins and make it very small, for example, let's make it 5 bins, we get something that is not at all representative of the PDF. If we make the number of bins very big, say 200, then we get a histogram that is very jagged. In this case, the software, removing the number of bins, chooses a reasonable bin width itself. Finally, let's have a look at kernel density estimators. Suppose that k of x is a non-negative function whose integral is 1, and for which the integral of xk of x dx is equal to 0. Now, the fact that k is non-negative with integral 1 means that it's the probability density function of a particular distribution, and the fact that this integral over here is 0, it means that the mean of this distribution is 0. In other words, the k of x is the probability density function of a distribution with mean 0, i.e. it is centered around 0. Such a function is called a kernel function. Further, let h greater or equal to 0 be a positive number, called the bandwidth. Suppose that a is greater or equal to 0. Then 1 over h k x minus a over h is also a density function, as you can easily verify using a change of variables. Moreover, this function is a scaled version of k of x. You have to move the graph of k of x a units to the right, then stretch the x-axis by a factor of 1 over h, and squash the y-axis by a factor of h. Now, because we've moved the graph of k a units to the right, the mean of this probability density function over here is a. As h gets bigger, this transformed density becomes wider, in other words it has a bigger standard deviation, and as h goes to 0, it becomes more concentrated at the point A. This is illustrated by the following graphs. Here we have k of x, a probability density function centered at 0. If we look at a half k of x plus 5 over 2, we have a equal to minus 5 and h is equal to 2. This shifts it 5 units to the left and squashes the y-axis by a factor of 2. So whereas the blue curve hit a height of nearly 0.4, the pink curve hits about 0.2. On the other hand, we can consider a case where h is equal to 0.5 and a is equal to 7. In this case, the density function that we obtain in that way is centered around the point 7, and it is much thinner, much more peaked. As you can see, in this case, the red curve goes up to about 0.8, which is double the height of the blue curve. Now let x1 up to xn be independent draws from a common distribution with probability density function f. The kernel density estimator, or KDE, with kernel k and bandwidth h is denoted as follows: f hat n of x is equal to 1 over nh times the sum of the kernel function evaluated at the points x minus xi over h. Here the subscript n indicates that we're dealing with a sample of size n. Now the empirical mass function has a point mass of 1 over n at each sample point xi. In other words, the probability that x is equal to xi is equal to 1 over n for the empirical mass function. The KDE has the effect of smoothing out each of these point masses. It takes into account all the points xi, but the points nearer to the point x have the greatest weight. This is because the function k x minus xi over h is centered around the point xi. The greater the bandwidth, the greater the impact of the xi away from x, and the smoother the corresponding density. There's therefore going to be a trade-off between smoothness and bias. Here we show KDE estimates of 100 standard normal variates. The true normal density function is shown in black. When we have a bandwidth of 0.1, this curve is shown in red and it's much too jagged. In other words, this bandwidth is too small. On the other hand, if we choose an h of 1, then we have a curve which is smoothed out too much. This h is too big. For the normal distribution, the so-called Silverman rule gives us an optimal bandwidth. That's shown in blue, and as you can see, closely approximates true distribution. As this is only 100 normal variates, it won't be exactly the same, but this KDE estimate in blue will more and more closely approximate the true distribution in black as n increases. Over here we show some commonly used kernels: the Gaussian, the rectangular, the triangular and the Panichnikov. Typically the choice of kernel function is actually unimportant, but the choice of bandwidth is crucial. Most software has built-in heuristics which choose an optimal bandwidth. Nevertheless, this does not always work well, and sometimes fitting by eye may be necessary. In other words, you need to play around with the bandwidth yourself and see what looks good. It can be shown that the KDE estimate of the density function approximates the true density function under the following conditions: when f is continuous at x, when the bandwidths go to 0 as n goes to infinity, but in such a way that n times the bandwidth approaches infinity as n goes to infinity. This is, for example, the case when h over n is 1 over the square root of n, which goes to 0 as n goes to infinity, but n times h over n is just equal to the square root of n, and that goes to infinity as n goes to infinity.